Starting the second half of this unit, we're going to start with the periodic law. The periodic law basically states that there are regular and repeating patterns that can be found within the periodic table. So there are patterns that you can learn about, and you can use these patterns in order to predict the properties of elements. Say I was to just randomly pick an element off the periodic table, and I was to ask you, tell me about this particular element, even though you had never seen it before. Based on the properties that are within this table, you will be able to predict many different physical and chemical properties of that element based solely on its location in the periodic table. And again, that refers to the periodic law, the regular and repeating patterns in the periodic table. All right, so we're going to start with how we use electron configuration in order to determine the order of the periodic table. So electron configuration can be used to explain the arrangement or order of the elements in the periodic table, the arrangements of electrons in the outermost, I did not leave myself enough space here, but outermost, that's an E, outermost energy levels are similar to the elements in the same group, meaning every single element in group 1 is going to have one electron on its outermost energy level. Every single element in group 2 is going to have 2 on its outermost energy level. Now, obviously, they have different numbers of energy levels, which again is determined by its period that it's located on. But everything in the second group right here will have 2, whether it has 1 or 2 or 3 energy levels. The outermost for all of these will contain the same number of valence electrons. And that's important because it doesn't matter how many electrons you have, it matters how many electrons you have on your outermost energy level, called the valence energy level. That is going to determine how you as an atom are going to behave. So, to go off of that, valence electrons, again, play the largest role in determining the chemical properties of an element. The inner ones, again, are not that important. They are shielded, they are blocked, they don't really do a whole lot when it comes to the behavior of particular atoms. Okay, so here again we have our period 1, which again is going to be your first row, period 2, period 3, period 4, the number of elements on those individual periods. So as you guys know, the period 1 only has a 1s suborbital. Period 2 has your 2s suborbital as well as a 2p suborbital. Period 3 has 3s and 3p. 4s has 3s, and then it goes back and fills up the third, the d suborbital of the third energy level. It'll go back and fill that new suborbital before it'll fill the 4p suborbital. 5, again, you have your 5s, 4d, 5p. On your 6th energy level, again, it's a little more complicated because you're down here. You have to go through the F block down here. Then you travel back up, go through your D block, and then finish going all the way through the P block. So it's a little more complicated. So from 6S, you go down to the 4Fs. That's supposed to be an F. And then your 5D, and then back to your 6P. Finally, period 7 is very similar to period 6. You're going to go to your 5F, then your 6D, finally your 7P. All right, so that's the electron arrangement within each of the periods of the periodic table. Okay. All right, so let's talk a little bit about the groups themselves. Now, group, again, is a term that refers to the column they are in. These are called periods, and again, they determine what energy level or how many energy levels they possess. These are called groups, and this is what determines the number of valence electrons it has on its outermost energy level. So the alkali metals are this very first group, group 1. All of these are called alkali metals, and they are very, very reactive, very reactive. So reactive, again, some of these cannot be found in their natural state. For example, francium down here, we've never really seen francium because it's so reactive, it doesn't stay by itself. We found francium containing compounds, but just a chunk of francium is not anything we're ever going to find because it's so incredibly reactive. Some of these up here are so reactive that if you drop a chunk of them into water, they'll actually explode. So that's how reactive I'm talking about. Alkaline earth metals are group 2 right here. Group 2, so this is the alkali. These are the alkaline earth metals. This again is group 2. They are reactive, but not quite as reactive. These are not explosive. Like hydrogen, of course, that's what brought down the Hindenburg, right? Very explosive. Alkaline earth metals, beryllium, magnesium, calcium, are reactive, but not nearly as reactive as your alkali metals. The next one we're going to talk about is we're going to jump all the way over to here to the 7th group, or 17th group, however you want to name it. The second to last one. These are called the halogens. So this is group 7. The halogens, again, are very reactive. For the non-metals, okay? They are not as reactive as your alkali metals. These do not explode in the presence of water or anything like that. But fluorine, chlorine, bromine, iodine, again, these right here in the second to last group are still quite reactive for the non-metals, okay? The last one, again, is our very last column over here, the very last column. Those are the noble gases. This is group 8. Sometimes referred to as 18, if you take in the D block into account. They are not reactive, none. They are like literally have no reactivity whatsoever. Again, this is where they get that noble name. They're kind of like snooty. They have their nose up to everybody else. They're too good for everybody else. They have a full outer energy level. They don't want to do anything with anything else. They are too good for you. Therefore, don't talk to them. Leave them alone. That's the way you want to think about them. They have a full outer energy level, therefore they do not want to steal anybody else's electrons, and they also do not want to lose any electrons, therefore they will not bond with anything. Now it says here, helium is a group 2 configuration, meaning it's a 1s2. Remember when we do electron configuration, you think of helium as actually being on the other side, but its properties resemble that of course, of the noble gases. I can't fit that, so I'm just going to say group 8. Group 8. So again, helium does belong over here because it is a noble gas. It has a full outer energy level. Therefore, its reactivity is identical to those of the other noble gases, meaning there isn't any reactivity. It has a full outer energy level, even though it's actually part of the S block, which is when we do electron configuration, we refer to it being over here. But it does, the element does belong over here because it has a full outer energy level and is non-reactive. It is inert, to use that word, just like the other noble gases. Okay, we already know about the S block, which is groups 1 and 2, the alkali metals and the alkaline earth metals next to them. Again, hydrogen is a group 1, but has properties similar to that of an alkali, even though it's actually a gas. P, of course, are your metals. Your P block are metals, also non-metals and metalloids. We'll talk about that very shortly. Your D block are what's called the transition metals. Their reactivity is very, very low. Basically, all the transition metals do is rust. They tarnish. They become discolored in the presence of moisture, but that's really about it. They don't really do a whole lot. They do make some compounds, but the worst thing you have to worry about them is whether they're going to tarnish and discolor. That's about it. Again, they do not explode in the presence of water, right? Finally, the F block, which is way the heck down here. This is your lanthanide and actinide series. Lanthanides and actinides. Again, these are not very commonly found naturally on Earth. Obviously, uranium is. There's a few other exceptions, but most of these are actually radioactive. And radioactive means that they have an unstable nucleus. They will degrade. They will undergo a transformation, which we will cover later. But they are unstable, and we call that radioactive.